We know that a relation is some type of relationship between an x and a y value on a graph. A function is a type of relation where there is only one y value for each x value. So in order to be a function, remember the graph has to pass that vertical line test, whereas you're moving your vertical line along the x-axis, each point on that graph is only hitting the line one time. We spent a lot of time in grade 10 dealing with linear functions. We're going to now switch into looking at quadratic functions, and the word quadratic is Latin for quadratum, which means square. In terms of algebra tiles, remember that this is our x squared piece. Each tile is named on the area. X times x gives us an area of x squared. So y equals x squared is an example of a quadratic function. All quadratics have a degree of 2. So let's graph this function and see what kind of a graph we get. So I can choose any values for x. I'm going to substitute them into the equation and determine the corresponding y value, which will give me my coordinate points that I can then plot on the graph. So I'm just going to, based on the way that my Cartesian plane is set up already, to make this simple, I'm just going to go with -2, -1, 0, +1, and +2 for my x values. So we're going to begin with our function, y equals x squared, and I'm going to substitute -2 in the place of x. -2 times -2 is going to give me a value of +4. So when x is -2, y is +4, and then let's go ahead and plot that. And then we're going to continue on. I don't need to show my substitution every time, but I'm going to now take x as -1. So -1 times -1 is going to give me a value of +1. So when x is -1, y is +1. Let's plot our second point, and we can also fill this in here. And now we're going to substitute in a 0 for x. So 0 squared is 0. So that is going to be right on my origin. When x is 0, y is 0. When x is 1, 1 squared is 1. So when x is 1, y is 1. And when x is 2, 2 squared gives me a value of 4. So when x is 2, y is 4. So let's plot that. And then we're going to try to connect our dots. And we could keep going and choose more dots, but I'm just going to show you. We're going to kind of look like this. So we're going to put our arrowheads on the end, and we're also going to make sure that we're never going straight up and down, because remember, then it's no longer a function. So we're going to kind of angle off to the side here. And this U-like shape, which is going to continue indefinitely, is what we call a parabola. It's a smooth, symmetrical curve that can open up like this one does, or it could also open down. Now, there's some specific terminology that we have to know when dealing with quadratics. So let's take a look at the various pieces here. We're going to begin with a vertex. So a vertex is either the lowest or highest point on a parabola. So in this particular case, my parabola opens up. So I have a lowest point here. Right there is my vertex. The axis of symmetry always passes through the vertex. It is a vertical line which is going to divide the graph into two equal pieces. So if we were to fold the parabola along that line, you're going to have two symmetrical parts. Remember that the equation of any vertical line is always x equals. So we're looking to see where does it cross the x-axis at, and because it passes through that vertex, it's going to always be the x-coordinate of the vertex. So I can see that in this particular case, I'm crossing at 0. So my equation for this graph of y equals x squared is going to just be that x equals 0. And it's always going to begin with x equals, and then look, where is it crossing the x-axis? We're going to have a minimum if we are opening up. You can see this is the lowest or the minimum point on the graph. We're going to have a maximum if we are opening down, because you can see here that this is going to be the maximum point on the graph. So in this parabola, y equals x squared, we can see that we have a minimum. And again, we're looking at the lowest point on that y-axis is going to be the y-coordinate of the vertex. So in this particular case, I have a minimum, and it's going to be at y equals 0. Just take your pencil and kind of run it along the y-axis, and you can see there's the first part of the graph. It is at y equals 0. Domain, because we have arrowheads on the end, in theory, we could choose values of x that were less than -2 or values of x that were greater than +2. So this graph is going to continue indefinitely. So if you do not have a context and all we're given is a function like this, then it's going to pretty much be x is an element of the reals if there is no context. So I'm just going to write that piece. I'm not going to write the full set notation. And then range, again, we're looking to see on the y-axis, there's my starting point at 0. 0, and it's going to continue up to positive infinity. So in this graph, we're going to say y is going to be greater than or equal to 0, and again, y is an element of the reals. Now, anytime we open up, we're always looking to see where is that y coordinate, and it's going to be every value greater than that. If we're opening down, such as this example, we can see that this is going to be the maximum, and it's going to be every value less than that. This is what we call the vertex form of a quadratic function. So we have x squared. It is a degree 2 equation. We also have some other variables in here, a, p, and q, which just represent numerical values. We're going to take a look at what does a, p, and q specifically control when it comes to graphing that quadratic. We have 3 examples of quadratic functions here. They all have a degree of 2, that's the highest exponent on the variable, and we're going to see what happens when we change some of the parameters in the function. So we remember that our y equals x squared, the a value is the number that comes right in front of x squared. Here I have an a value of 1. I can't have a 0 or that whole piece is gone and it's no longer degree 2, it's no longer a quadratic. This one has an a value of 2, a value of -2, and an a value of 1/2. So we're going to do this one at a time by changing each a value and then seeing how that impacts the graph. So I'm going to re-put my original graph here just so we have something to compare it to. And then same concept, we're going to sketch a table of values. I'm going to keep my x values the same. We're going to substitute in for x and then generate our y values to get those coordinate points. All right, so in our first one, y equals 2x squared, I'm going to take my function. I'm going to substitute in a -2 in the place for x. -2 squared is +4. +4 times 2 is 8. So when x is -2, y is 8. So we've gone ahead, x is -2, and then we've gone up 1, 2, 3, 4, 5, 6, 7, 8, and there is our first coordinate point. We're going to continue on filling in that table of values. We don't have to write it out every time. We're going to mentally substitute this in. So for example, -1 squared, -1 times -1 is +1. +1 times 2 is 2. So I know when x is -1, y is 2. So x is -1, y is 2. Let's put that in there. When x is 0, 0 squared is 0 times 2 is still 0. So that's going to be right on the origin. And then if I substitute in a 1, 1 squared is 1. 1 times 2 is again 2. And you should notice here now, we know that a parabola is symmetrical. So once I know that it's going to have a vertex right here, I know that those points are always going to be across from each other. So that also tells me that when x is +2, it's going to have a value of 8 as well. So you could either algebraically put it in there or you could reason this out. So x is +2 and y is +8. And then again, it's really hard with this one because it's kind of skinny, but try not to go straight up and down. So we're going to connect it somewhat like that. Put your arrows on the end because again, we could keep going. If I were to substitute in a 3 for x, then I would have 3 squared is 9. 9 times 2 is going to give me 18. And we can see the graph isn't quite drawn large enough, but if x is 3, 18 is going to be way up here. So it's going to kind of pull up as we go along. We're now going to change the a value to a -2 and see what happens. So again, I'm going to take my original function that's given to me. I'm going to use the same values for x. So substitute in a -2. -2 squared is +4 times -2 is -8. So now when x is -2, y is -8, there's our first coordinate point on this graph. So what do you think is going to happen to this parabola? I'm going to get you to go ahead and fill it in, and then you can keep going with this one as well. Get those last 2 graphs sketched, and then we'll take a look and make some predictions. What do we think the a value controls when determining that graph? All right, how did we do here? So y equals x squared is what we call our parent function. It's the simplest form of a quadratic. I'm going to kind of box this off so we can compare it to the others. The first thing I want you to notice is what's the difference between having a negative a value versus the other 3 which are positive a values. And you should notice that when we have a negative a value, my parabola now opens down. The a value determines the direction of opening. So if a is negative, we open down. If a is positive, all of those graphs are opening up. The second thing is how wide or narrow that graph is. As soon as we have a 2, you can see that this graph becomes much narrower because that 2 coefficient is making these y values pull up. So it's kind of stretching vertically that graph. Whereas as soon as we have a value that's between 0 and 1, we can see that the graph is shrinking. So I actually added a 3 in here just so you could compare it to what we had back here. And you can see how now, because we're always taking half of that value, it's going to kind of compress the graph. graph. Okay, so I'm just going to scoot to the end here. And A value is what we just investigated. We know that it controls two things. Number one, the direction of opening. If A is positive, our parabola opens up. If A is negative, our parabola opens down. And it also controls the width or the narrowness of that parabola. If the absolute value of A is greater than 1, so absolute value means you take the positive value of A. So if you ignore the sign and just take that value, anytime A is greater than 1, we're going to expand vertically. Our parabola is going to therefore get narrower. If the absolute value of A is less than 1, so basically if A is between 0 and 1, our graph is going to compress and therefore get wider. We're now going to investigate the value of P. So you'll notice that P is the value that occurs within the brackets. So you can see in my parent function, I don't have any brackets, which means my P value is 0. So we can continue on with our table of values to generate some coordinate points. If I substitute a -2 in here, -2 minus 2 is -4. -4 squared gives me a value of 16. So I can continue on and get those points. I can also go in here and graph this. So we've got x, make sure you do -2, close the brackets, squared. My window is just the default, -10 to +10 with a scale of 1 on both the x and y axis. And then you can press graph to see what this parabola will look like. So I've gone ahead and plotted most of these points by hand. I left this one off because it's out of the Cartesian plane that we have drawn here. But I can kind of now compare and say, if I wanted to say second function trace, remember that number 1 lets us put in any value for x. So let's try maybe when x is 3, we can put that in. Y is going to be 1. So I know when x is 3, y is going to be 1. That tells me that this is going to be my vertex. The axis of symmetry will run through it, and then this graph is going to be symmetrical on the right-hand side. So that allows me to finish sketching the parabola. Then I've gone ahead for my next one, and I just went in here and changed this to a plus sign, and then we can graph that one to see what the shape will look like. We can also get some points using a table of values, and then that's enough to get the sketch for that graph. So what does P control? Well, if we go back to the parent graph, we can see that the vertex is on the origin. My vertex is now shifted 2 units to the right when P has a value of 2. My vertex is shifted 2 units to the left when P has a value of -2. And I wrote this out here just because we have a +2, but remember, minus times a negative times a negative gives us that positive value. So P is shifting the graph horizontally. It's what we call a horizontal translation. The value of P is how many units we shift that parent graph either to the left or to the right. And anything in brackets behaves the opposite of what we think it will. So normally if we see a negative, we think we're moving to the left because the negative numbers are to the left of the origin. But in this case, because we have a minus here, P is +2, so we're shifting to the right 2 units. P is actually a -2 here, so we are shifting to the left. So just remember, anything in brackets kind of behaves the opposite of what we think it will. So once again, we're going to scoot over to the end. P, the value in brackets, is the horizontal translation. So it's the number of units our graph shifts left or right horizontally. And just remember, if we see a plus P, we're shifting our graph to the left. If we have a minus P, we're shifting that parabola to the right. And finally, we're going to investigate what Q does. Q is the number outside of the bracket. So in this particular case, Q is 3, Q is -3, and here, because we don't have anything added or subtracted outside of the bracket, we have Q is equal to 0. So we need to get some points here. We can draw a table of values, we can use our calculator, but if I take a look at this, I know that if I put a 0 in for x, this term is 0, plus 3 gives me a y value of 3. So when x is 0, y is 3. So let's go ahead and plot that point. And then 1 is an easy number to work with. So I know 1 squared is 1, plus 3 is 4. So when x is 1, I know I'm going to have a y value of +4. And likewise, -1 squared is also 1, plus 3 is going to give me 4 as well. So when x is -1, y is going to be +1. And then we can go ahead and get a few more points if you want. So 2 squared is 4, plus 3 is 7. So we have 2, and then it's going to be about here. And because I can now see that this is going to be symmetrical, the vertex is going to be at 0, 3, I can go ahead and plot that point, and then we're going to join those in a smooth U-like shape. And then we can go ahead and do the same thing with our last graph. So again, if I put a 0 here, that term is gone, and I have -3. So when x is 0, y is -3. 1 squared is 1. minus 3 is negative 2. So I've got when x is 1, y is negative 2. Likewise, when x is negative 1, y is also negative 2. If I put a 2 in, 2 squared is 4 minus 3 is positive 1. And I can see now it's going to be symmetrical about the vertex. So I can then go ahead and sketch my other side. So in terms of Q, go back to the parent function, and we can see that all three of these graphs have the same shape. The difference is the position of the graph. My origin in my parent graph is at 0, 0. Here we can see it's moved up to 3. Here we can see it's moved down to negative 3. And then take a look at the function. Q is positive 3. We've moved up 3 units. Q is negative 3. We've moved down 3 units. So Q is what we call the vertical translation, and that behaves as it should. So we would expect that when Q is greater than 0, we're moving up. We would expect that when Q is negative, we're moving down. Q is the number of units that we're moving that graph. So when we put this all together, we have y equals a times x minus p squared plus q. That's what we call the vertex form of a quadratic. A controls which way we open, as well as how wide or narrow that graph is. P, how many units did we shift left or right? Q, how many units did we shift up or down? Most important of all, why do you think this is called the vertex form of a quadratic? Go back and take a look at some of the graphs we originally sketched. P is inside the bracket. Q is the value we add or subtract to that in vertex form. In my parent function, I have no bracket. P is 0. There's no piece I'm adding or subtracting on. Q is 0. My vertex is 0, 0 on that graph. My next one, again, there's no bracket. P is 0. There's nothing I'm adding or subtracting to that function. Q is 0. Again, my vertex is 0, 0 for both of those. When I scoot down here, I can see that P has a value of positive 2. Q has a value of 0. Positive 2, 0. Here, remember, this is minus a negative 2, which gives me that positive 2. So P is negative 2, Q is 0, negative 2, and 0. Now in this particular function, we don't have any brackets, so that tells me P is 0, Q, the piece that we add or subtract to that, is 3. So 0, 3. Here again, no bracket, that tells me P is 0, Q is negative 3. And look at that, 0, negative 3. So P is the x-coordinate of the vertex. Q is the y-coordinate of the vertex. This is called vertex form because it gives us the coordinate point of our vertex. I'm going to take a look at a few examples here, beginning with some found in our textbook. We're given a function and we have to say how we can get that graph from our parent graph. We can always draw a sketch. We recognize that this is a quadratic, so we know it's going to have the shape of a parabola. I also know that there is no brackets and there is no piece that I'm adding or subtracting to it. So that tells me my vertex is going to be 0, 0. So I can go ahead and plot that. I also know that because my a value is positive, I'm going to be opening up. And because it's less than 1, I know I'm going to have a fairly narrow parabola. So it's not super precise, but it's enough to give me some information. Now, anytime you have to state a whole bunch of things, particularly if we have multiple questions we're doing, I would probably set up a table and then we can just go along and fill in if you have to do B, C, etc. All right, so now I can tell from my diagram as well as from the function, A is positive. That tells me I'm going to open up. If I open up, I have a minimum value, and so that's my minimum value. And then the range along the y-axis, y is going to be equal to 0 and every value greater than 0. So in set notation, range is a set of y values such that y is greater than or equal to 0 and y is an element of the real number system. In the next example, we're asked to compare these two functions. I know they're both going to be quadratic functions because they're both degree 2. So this is my parent function. I can see that we're shifting the graph up 1 unit. So if we go ahead and draw this graph, I know that my vertex is going to be at 0, 1 because I don't have a p-value. There's no brackets there, and Q is that 1. So let's go ahead and plot that point. I also know we're going to open up because A is positive, and we can always get some other points here. So if x is 1, 1 squared is 1, plus 1 is 2. So when x is 1, y is 2, and I know it's going to be symmetrical about that axis. So we can always go ahead and get some more, but let's just draw a rough sketch. So the vertex we already established is at 0, 1. We can get that from the function. The axis of symmetry, remember it's always going to be a vertical line. Any vertical line begins with x equals, and we can see that we're crossing the x-axis at 0. It's always going to be the x-coordinate of the vertex, so the axis of symmetry x equals 0. Domain, we're going to continue to negative infinity as well as positive infinity. So in set notation, we have a set of x, where x is an element of the real numbers. Range, if we take a look at the y-axis, we start at positive 1, and it's every value greater than that. So we're going to have y is greater than or equal to 1, and y is an element of the real numbers. We can tell from our sketch that we will have no x-intercepts. The y-intercept always occurs when x is 0. We're crossing the y-axis at 1. With our next example, we're going to begin by sketching this function. So I can see that this is vertex form. I know my vertex is going to be positive 3, positive 9. So we can actually go ahead and fill that into the chart as well as plot that. And then we also know that the axis of symmetry is always going to pass through that vertex. So in this particular case, it's going to cross the x-axis at positive 3. It's always crossing at that x-coordinate of the vertex. So the equation of that line, always write it as an equation. We have x equals 3. We can see that because a is negative, we know the parabola is going to be opening down, which means we also have a maximum value. The domain, because we don't have a context, this function is always going to be x as an element of the reals. We also know it's going to be less than that maximum value of 9. So it's going to be less than or equal to 9, and y is an element of the real number system. Now, in terms of the x and the y-intercepts, there's two ways you could go about getting those x-intercepts. One way we could do this is by graphing. So I've just entered negative and then x minus 3 squared plus 9 into my calculator. I kept the default settings for the window. And then if we go into second function trace, number 2 is zeros. Those are the x-intercepts, and your calculator prompts you. So we have to do these one at a time. So if I start with the one on the left, it says, are we to the left of that intercept? So right now my cursor is at 0, 0. I'm only ever going to move left or right. If I go up and down, it takes me off the graph. So I'm just going to scoot over here. So I'm currently on the left. I'm going to press enter to say yes. It says, are we to the right of that intercept? So I'm going to just scoot my cursor over so that I'm to the right. I'm going to press enter to say yes. And then it says, do you want me to guess in this range where those arrows are? I'm going to say yes one more time. And we can see that this here is negative 4.44 times 10 to the power of negative 14. So that's essentially like 0, and y is 0. So my first x-intercept is 0, 0. And now we're going to do this again. Second function trace, and we're going to go to number 2 zeros. Now this time I'm doing this one. So it says, are we to the left of that? So I need to get fairly close. So we're going to scoot the cursor all the way over here so that now I'm on the left. We're going to press enter. It says, are we on the right? So you're going to imagine if there's a vertical line passing through that. I'm now to the right of this vertical line. I need to be where y is negative. I'm going to say enter. And then do you want me to guess? And again, it's going to be guessing within that range. So we're going to say enter. And my second x-intercept is 6. We can also go about this algebraically because we know x-intercepts occur when y is equal to 0. So if I take my original function, we can actually substitute in a 0 for the place of y and then algebraically rearrange this to isolate x. So the first thing we're going to do, remember we're doing order of operations in reverse. We're going to remove any piece that we're adding or subtracting. So I'm going to bring this 9 to 0 by subtracting 9 from both sides. 0 minus 9 will give me negative 9. We're then going to remove any piece that we're either multiplying or dividing. So right now I need to get rid of this negative 1 because we're multiplying negative 1 times that piece with the variable. So I'm going to divide out the negative 1, and I'm going to do the same thing to the other side to keep it balanced. Negative 9 divided by negative 1 is going to give me positive 9, and then I need to get rid of that squared, so we can square root to get rid of a squared, and I'm going to do the same thing over here. Now because we have a variable in here, we can either end up with a positive or a negative root, so I'm going to put plus or minus there, and then remember when we do this, square rooting cancels a squared, and so go ahead and we're going to get x minus 3. So let's remove these brackets, and then to isolate x, we can add 3 to both sides. So the square root of 9 is 3, so we're going to end up here with positive or negative 3 plus 3. And then if we finish this off, we've got positive 3 plus 3 is going to give us 6. Negative 3 plus 3 is going to give us 0. So we have two x-intercepts, and again, you can check on the graph. One is going to be at 0, The other one is going to be at positive 6. And then in terms of the y-intercept, we know a y-intercept occurs when x is 0. So I'll show you on the calculator first. If we go second function trace again, we can put in number 1 as value, so that lets us enter any value for x. So we know the y-intercept will occur when x is 0. So there you go, 0, 0, that's where we're going to cross the y-axis. If we do it algebraically, similar concept, we're going to substitute in a 0 in the place of the x, and then I'm going to begin, because my y is already isolated, we're just going to do order of operations. 0 minus 3 is going to give me negative 3 in brackets. Negative 3 squared is positive 9, so we're going to have negative times positive 9 plus 9, so this is going to be negative 9 plus 9 will give me a value of 0. So my y-intercept occurs when y is 0, right there on the graph. And now you can go ahead and plot those points on our sketch, and then just to check to make sure, is this graph symmetrical, about that axis of symmetry, and does everything kind of fit together?